quantized six-vertex model on the torus.
Yeah.
This.
So thank you, Mari and Vladimir, for the invitation. It's very honored to speak in this member of conference. So my talk today is based on this paper with Inoue-san, Terashima-san, and Yagi-san, which we posted a few months ago. So what is quantized six-vertex model? What is the quantized six-vertex model? It's a 3D lattice model with the following features. By the way, so the 3D lattice model is, of course, the topic that Rodney was the pioneer of the pioneer. So in a sense, my talk is kind of dedicated to that sort of development. So it's defined on a so-called atomic graph. I'll explain about this. Atomic graph G on the torus. And the layer transfer matrix with two spectral parameters form a commuting family like this. And its commutativity is assured by several kinds of tetrahedron equations. And it can also be formulated as quantized diamond models and includes so-called free parafermions and relativistic to the chain and so on. So these free parafermions, probably named by Paul Henry, was also the invention of Motley in late 80s. So let me begin with the building block of the quantized six-vertex model. This is essentially due to the Vladimir and Sergey. And also I work on a little bit. So let V be a two-dimensional vector space. And WQ, which also appeared in the previous talk, is a QI algebra. So it's just a Q computation with the Q computation relations. And this 3D L operator is linear operator acting on V tensor V, whose matrix elements take values in WQ. And more specifically, I only allow these 6 patterns with respect to this component. So this is obviously 6-vertex, as usual. But boson weights are not C numbers, but they belong to the QI algebra by this rule. And R, S, F, G are free parameters, which is commuting free parameters. So sometimes, or quite often, I will denote this object by this diagram, where this black arrows takes values in this space P. So the black arrow takes just 0 or 1, but this blue arrow means that QI algebra. So the immediate question is, does this 6-vertex satisfy the Yang-Baxter equation? The short answer is no, but instead it satisfies the tetrahedron equation. So let Lijk be the denote L operator acting on these tensor components. Then it is satisfied this form of the tetrahedron equations, which is sometimes called RLL type. And so this object is a fundamental object, but I'm not going to talk about this guy in this talk. Maybe I'll mention it briefly in the very end of my talk. But pictorially, it's like the Yang-Baxter equation, it's represented as a reversal of the triangle, reversal of the tetrahedron. So remember that these black arrows are two-dimensional and blue arrows are QI algebras. So if you forget about these 4, 5, 6 spaces, then you return to the original Yang-Baxter equation. So in a sense, this relation is Yang-Baxter equation up to conjugation. Or in a sense that Boltzmann-Waiter operators, we may refer to it as a quantized Yang-Baxter equation. So using that building block, I now consider the n by n square lattice like this. And so each vertex is a 3D operator. In that sense, Boltzmann-Waiter QI algebra values, or I should say tensor product QI algebras. So at each vertex of this n by n square lattice, I introduce an independent commuting QI algebras. So, and now I further introduce some boundary magnetic fields. So X and Y are parameters, which will play the role of spectral parameters. But this H is very simple operator. So it's just count the number 1 in this two-dimensional vector space. Later, I will also let H act on the QI algebra by this rule. So it counts the number of exponential W, so on. But anyway, so this is the basic configuration. And now I consider 2D partition function with fixed boundaries in this arrangement. And that will give us a so-called monodromy matrix. And if I sum over the 2D boundaries and the periodic boundary condition, then I will get the layer transform matrix depending on X and Y. So let me explain more concretely. So monodromy matrix acts on the this space VI where I employ this notation. So these VI indices specify this vector which lives in the V2 to M. And Vj here. So it's transfer from southwest to northeast by this manner, where I have this boundary magnetic field powers and also the matrix elements lives in the QI algebra tensor every times M like this. So when M and N is equal to 2, so yeah, if I number the QI algebra 1, 2, 3, 4 like this, then the layer transfer matrix is a polynomial in X and Y whose coefficients as in general non-commuting coefficients are taken value in QI algebra tensor 4 because there are 4 vertices. And also it depends on the parameters F, G, R. So as I said, this exponential use and exponential doubles are Q commuting. It's not obvious that they are commuting, but the statement is they are indeed commuting and how it comes. So let's prepare for the proof of the commutativity. So L, I already explained, that's a 3D L operator. And I introduced another companion 3D L operator, which I denote by M. So the definition is very simple. I just replace the parameter by their primes, but also replace the parameter Q by minus Q. So that means this is also another 6-vertex like quantized 6-vertex like things, but now the exponential U and the exponential W contained in this operator is minus Q commute. That's a bit technical. But anyway, so in order to distinguish this WQ and W minus Q, I use green arrow here for M. And IJK means number of components. Then, it was, I think the discovery was just again brand new that they satisfy the tetrahedron equation, MMLL type, denoted like this. So for example, this piece 2, 4, 5 is, I think, let's go to that. M1 to 6, so it's here. Yeah. And then 3, 4, 6, it's 3, 4, 3, 4, 6 is here. Sorry. The 1, 2, 6 is here. And the 1, 3, 5 is here. And the 2, 4, 5 is here. So what this equation is doing, if you push this green arrow through the blue arrow, then the order of the multiplication along this blue arrow gets interchanged. So this vertex comes first here, and this vertex becomes both. So that's a MLL type tetrahedron. And another bit technical remark is these operators N satisfy in the so-called weight preserving property. So as I said, that the H is a just number counting operator, and this relation can be depicted in this manner. So where you can push this magnetic field operator through the vertex, provided that the associated spectral parameter has this specific relation to X, Y, and Y. This is a so-called weight preserving property. So using these things, let me illustrate how the commutativity forms. So the proof, I combine 2 MN copies of L operator. So in the front layer, I have MN copy of L operator, blue arrows. And also in the back layer, I have the same number of L operator, and I compose it along these blue arrows. So these parts constitute an EM copy of L. But I also put the green wire at the edge, like here. So this is length M and the length N and length M. So there are M plus N copies of green arrow. And I apply the tetrahedron equations to move the green arrow from northeast to southwest. As I said, if you push this arrow like this, then you can change the front layer and back layer. So, and the good thing about this is like Young-Bak's equation, you can push it again and again until you completely penetrate 2 layers like this. And so later I will refer to such a maneuver in terms of 2D projection like this. So if you look along this blue arrow, then it looks like the movement of the green arrow through the black parts like this. So that's the first step. Now I multiply the boundary magnetic fields to these parts on both sides and apply the so-called weight conservation on the left-hand side. So what was the weight conservation? So it was like this. You can push the magnetic field inside somehow. So that gives me this object. This is the and now there is a minor step. I dislike this boundary magnetic field. So I move it to the right-hand side by multiplying their inverses like this. So here we have such equality like this. And now that I take the trace over the so-called non-negative mode representation of these green arrow, I'm not going to explain the detail of this non-negative mode representation, but anyway, so there are such good representation where you can identify this trace object or green tube, I should say, is nothing but the quantum R matrix associated with, I'm losing a pattern, associated with U minus Q inverse S n plus n hat. And the most fundamental facts about it is it's invertible. So this relation has already, I'm losing one. But so we have the product of the 2 monodromy matrices and followed by this green part like this and like this. So this is quite analogous to the usual 2D situation. But because this R matrix is invertible, so I can multiply R inverse from the right to the both sides and take the trace with respect to the auxiliary space. So auxiliary space is these black arrows. And that gives us nothing but this commutation relation.
Which representation?
Yeah. You mean this representation? You mean non-negative model representation?
No, I mean the UQ7.
Yeah, that's a reducible representation in general. So it's a direct sum of all the fundamental representation. Yeah, probably you know. So yeah, so that's the story about the homogeneous or kind of n by n square lattice setting. But we can generalize it to the more general admissive graphs. So what is admissive graph? Before defining those graphs, I should mention that tetrahedral equations, which will be necessary to prove the commutativity in such generalization. So I use this alternate type tetrahedral equation here. Can I change the battery? So I
think it's going flat already.
Yeah. Maybe. Can you see still this pointer?
I think the battery is gone. I only put a new one in this morning.
You'll have to use the arrows
Oh, okay.
and then I'll take.
Yeah. Can you see the cursor?
Yes.
Yeah. So this was tetrahedral equations that I have been discussing. But yeah, actually there are more such relatives of such tetrahedral equations. So here I reverse the orientation of the horizontal line. So that's what I call horizontally reverse type. And similarly, in this case, I reverse the orientation for the vertical arrows, which I call the vertical reverse type. This is totally reverse type. So, and also we need a sort of inversion relations. That's sort of detail. So I'm not going to explain the detail, but anyway, so I remember that this blue arrow carries the parameter RSFG. It's the original 3D L operator. But M green arrow is denoted by, and it depends on the parameters, those R prime, S prime, G prime. The remarkable thing is this O and T doesn't require any parameter relation, but H and V, we need to set this, impose this parameter relation. R prime is equal to S prime, G prime is equal to Q times F prime, and so on. Thank you. Yeah, that's. So, yeah, let's summarize those many types of tetrahedral equations and integral relations. So I group it into 3 types. So first type, I need such parameter relations for the parameter attached to these green arrows, R prime, S prime, like this. And type B is different relations. So these different 2 types. So this type, what is that? These O and AT don't require any conditions for these parameters, like this. So this is type N, type B, and types. So the fact that conditions on the parameters in type A and B are different, so you see they are different due to factor Q inverse here, but Q here, motivates our definition of admissible graph on the next page. So the definition of admissible graph. Let G be a directed graph on the torus. So that means exactly 2 wires meet at each crossing. We never allow the 3 wires or more wires intersect at one point. So the G is admissible if the initial northeast arrow can be moved to the final southwest arrow by applying the A type of moves where type A and B do not coexist. So there are 8 types of moves, 1, 2, 3, 4, 5, 6, 7, 8. But if you can move those green arrows from northeast to southwest without mixing type A and type B, because these parameter conditions are different. So this is an example of admissible graph, and this is an example of non-admissible graph. Now, our theorem is if G is admissible, then the associated layer transfer matrix commute. And the conjecture is, so it should be good. It will be good if we have very simple, describable, sufficient condition of the admissibility. So that's our conjecture. If G includes no oriented phase, then it is admissible. For example, this is oriented loop. Look, here it's oriented loop. And then it's no admissible. Here there is no oriented loop. But anyway, so this is an example of the admissible. So given this configuration, well, I'm discussing about this admissible example, and I'm going to show you that it's indeed possible to transform the northeast arrow, green arrow here to here by only using type A. So this is the initial northeast arrow, and I topologically deform it. And at certain points, I have to pass this. I have to let this green arrow pass through the black vertices. So every time I apply this transformation, I only use a type H and horizontal reverse type and ordinary type and so on to go to this place. And so that doesn't mix type and A and B, and that's the reason why it's admissible. So this is another example of the admissible G and associated commuting layer transfer matrix. So I'm considering the quantized 6-vertex model defined on this admissible graph with relative boundary condition. And so TG is the polynomial in the X and Y in this manner. Well, these terms are rather trivial, just describe coefficient, but the coefficient of Y and Y squared X, XY is non-trivial and given by this QY generators like this. But since TG forms a 2-parameter commuting family, these P's are all commuting. So they are the kind of commuting, they define the commuting Hamiltonians quotation mark, living in tensor products of the QY. So there is an obvious inhomogeneous generalizations keeping the commutativity. So the first one is those boundary magnetic field. I put probably Y to the H here, and X to the H here. But I can also introduce a kind of parameters attached to each wires or arrows like this. So the single X can become the kind of multi. So X, so here this this can be replaced by y times nu1, and this can be replaced by y times nu2. I mean, the boundary magnet can be replaced in that manner. Still, this commutativity is kept. And RSFG are also attached to each 3D L operator to these, so they are living on these vertices. But that can be chosen also depending on the vertex, like this. So I show this give this commuting currents, but these F and G can be replaced by more kind of involved product of F1, G2, and S3, and R4, and that's also. So this inhomogeneous generalization has some advantage to capture the known, actually the celebrated free power parameters. So that was goes back to the Rosenbach's in '89 paper and studied by many people. So so in this case, I take such G. So it almost looks 2 by L square lattice, but the orientation is somewhat different. So here it's upright arrows, but this is left pointing arrow, and this is right pointing arrow. Again, I'm losing. But at the end, these mu and mu prime are inhomogeneity in the boundary magnetic field. Moreover, as I said, RSFG parameters can be chosen arbitrarily depending on the vertices. So on the first law, I choose F parameters 0. And on the second law, I choose G parameters 0. So that certainly restricts the possible 6-vertex configuration significantly. So, and especially I further focus on the case where mu and mu prime are 0. Then that kills one of the spectral parameter, and I get the TGY. And it can be expanded in this manner, where JM is a commuting. And when L is 3, for example, J1 consists of 4 terms, and which correspond to these figures I'm looking at. So this solid line means the 6-vertex configuration, and well, you're all familiar with the 6-vertex configuration is a line configuration. So in that sense, so it's a 6-vertex, but line configuration like this correspond to the H1, H2, and the H3 and H4. So that's this strange winding is due to the choice of this reverse orientation in the top law and second. And so this configuration has quantized boson weights. The boson weights taking the value in the QY large. So it can be represented completely in this manner, where X and Z's are given in this manner, in this formula. So again, I'm losing some data to switch these operators. And obviously, they obey the Q-square commutation relations. And for L general, the situation is similar. So I introduce H operator, H odd operator, and H even operator. By the way, this H has nothing to do with the weight operator that I have introduced previously. But anyway, if I call these two combinations by H odd and H even, then they satisfy such Q commuting relations. And for general L, this formula generalized as follows. So JM takes this formula where this fancy inequality is defined by this rule. And especially this J1 is just a summation of HAs. And due to the definition, it becomes like this. And the commutativity of the layer transfer matrix implies that they are all commuting. And we find that this JM reproduces exactly the free fermion Hamiltonian when M is equal to 1, and it's higher order conserved quantity for M general, which was firstly obtained by Paul Fendry in 2014, when Q square is specialized to the primitive nth rule of unity, and the following representation is taken. So I recall you that X and J's, X and Z's obtain satisfy this commutation relation. So this is when Q square is the n float of unity, you can consider the finite dimensional representation of this sub-algebra of the whole tensor product of QI algebra. So that reproduces the free parafermions. So at the moment, I don't know what's the benefit of this reproduction of the free parafermions, but at least I can say that depending on by considering more general admissible graphs, we can embed these free parafermions in more general kind of, or we can consider more general free parafermion like commuting Hamiltonians rather systematically by looking for such admissible graphs. So I'm almost done. So let me summarize and plus alpha. So the quantized six-vertex model on admissible graph G on the torus that I explained. So it has a commuting layer transfer matrix with two spectral parameters. And TG itself belongs to the tensor product of QY algebra attached to each vertex I of G. And the commutativity is ensured by the several kinds of tetrahedron equations for the 3D L operators. So I didn't talk about the R operator intertwining three product of 3D L operators, but it has a very interesting story related to the quantized quantum cluster algebra of symmetric butterfly quiver. So that I won't talk today, but yeah, that's a remark. And also I explained the free parafermions, but by considering some other admissible graph, we can reproduce the so-called relativistic to the chain and also the diamond model like this. So that's essentially the end of the talk. So I think probably in yesterday's talk by Mari, so this photo was already shown that, yeah. And so this is Rodney's signature in his 2007 edition of his book. And his family very family fondly remembered. Thank you.
Do anyone have any questions? Just looking online, is anything bad? But no one? What? Yes.
Yeah. What about the 3D models? I mean, you were talking about 3D relation, and in the end, you needed those only for the commutativity of the for the transfer matrices of the 2D models. I mean,
well,
you construct
3D. Yeah, well, this trans-TG is a transfer matrix for 3D models. So it's the transfer one layer to the another layer. So if you take the product of them, you pile up the lattice and you get three lattice.
Yes.
So, but it's very anisotropic. So on this layer, it's six-vertex, two-dimensional kind of model, two-state models. But in the perpendicular directions, you have QI algebras. So once you choose some specific representation of the QI algebra, so you get some multi-state model in that direction. So in that sense, it's quite anisotropic.
Okay. Yes.
So, well, you can view three-dimensional model as two-dimensional if you look in the right direction along the third axis. So you want to see the third dimension. Well, then there are no more speakers, so let's thank the speaker.
Thank you.